Okay, let's dive straight into this explainer and master exactly how to tackle Cambridge Computer Science exam questions by looking at the precise moments where students are losing massive marks. Picture this scenario. You are sitting right there in the exam hall. The clock is relentlessly ticking down. You can practically hear that tension-building music in your head, right? You turn the page and boom! There's a massive, intimidating 8-mark question on data representation. Specifically, it's asking you to evaluate text, sound, image, and video storage. Now, if you're taking Cambridge syllabuses like 0417, 0478, 2210, or even AS Level 9618, you know exactly the kind of question I'm talking about. Now I want you to consider two very different types of students taking this exact same exam. On the one hand, we have Alex. Alex is a famously hard worker. He studies for hours, but he overloads his answers with raw, unfiltered computer science facts. He basically dumps every single thing he knows about binary, hexadecimals, and pixels onto the page, but there is absolutely zero analysis of the specific scenario the examiner asked about. On the other hand, we have Sam. Sam is always rushing against the clock. Sam sees the word video in the prompt, completely ignores the command words at the start of the sentence, and just hastily scribbles down MP4 along with a couple of really vague bullet points. So what actually happens when the examiner gets these papers? We see the red pen marks bleeding all over both of their exams. They both lose massive, easy marks, despite knowing the underlying topic. Well, in our session today, we are going to completely transform those harsh red marks into beautiful green check marks. Let's get into it.
Now, what's really fascinating about this specific question is that memorizing giant vocabulary lists just isn't enough anymore. It really isn't, because what happens is students often recognize a familiar term in the prompt, their brain lights up, and they end up answering a completely different question than the one that was actually asked. Let's look back at Alex's approach for a second. The exam question specifically asked why a high-resolution video file requires compression before being transmitted over a network. Alex wrote a flawless, literal textbook definition of what a pixel is, what color depth means, and how resolution works. He wrote a perfect paragraph. But did Alex actually answer the question about network transmission? No way. He didn't mention bandwidth, he didn't mention transmission speeds, and he didn't talk about latency. 0 marks for context. Then we look at Sam. Sam rushed and entirely missed the critical command word evaluate. Sam just confidently stated that video files are big. But listen, the examiner isn't looking for a human dictionary. They are testing your understanding of the core mechanism and your ability to apply it to a real system. You can literally memorize the entire textbook front to back, but if you don't know how to decode the specific assessment objectives of Cambridge exams, you are leaving guaranteed points on the table. This is, without a doubt, the single biggest trap in computer science examinations today.
Section 1. The 3 layers of learning. We need to look at exactly how to move from those simple, isolated definitions to complete and total exam mastery. This is where we reveal the ultimate strategy. To permanently fix this memorization trap, we need to completely rethink how we learn and process this information. We have to use a framework that actively moves you from a basic conversational understanding to total, undeniable exam readiness. The complex topics of text, sound, image, and video storage should absolutely never be taught or revised as isolated definitions. They are part of a much larger, totally connected digital ecosystem. So, the absolutely crucial point here is that students usually fail because they stop at layer 2. They genuinely think they know a topic inside and out until they are suddenly forced to express it as an exam-shaped response under incredibly strict time pressure. Think about it like this. Layer 1 is your everyday language. This is where you say, well, videos take up a lot of space on my phone. Layer 2 is technical vocabulary. This is stepping it up to high resolution and high color depth increase the overall file size in bytes. That's better, right? But Layer 3 is the exam-shaped response. This is where the top-tier students use the PEEL framework, Point, Evidence, Explanation, Link. They make a highly specific point about storage, they provide solid evidence using the exact scenario given in the exam question, they explain the underlying technical mechanism, like distinguishing between lossy versus lossless compression algorithms, and finally, they link it all back directly to the exact command word the examiner used. Using the PEEL framework is exactly how you jump from Layer 2 to Layer 3 and start securing those top-grade boundaries. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Section 2. Description versus explanation. Pay close attention here, because this is the exact boundary where the highest number of marks are lost across the entire syllabus. This is where the real transformation of your exam technique begins.
This entire concept is all about successfully decoding command words.
On your Cambridge paper, the words state, describe, and explain are not just synonyms. They demand completely different levels of cognitive effort from you. If a question asks you to state what a pixel is, a quick few words will do the trick. But if you see the word describe, you need to literally paint a picture in words of the specific characteristics of that exact data type. And when you see explain, the stakes are at their absolute highest. You must provide the underlying reasoning. Why is this process happening? How exactly is it happening? What is the technical consequence? This brilliantly illustrates exactly what examiners see when they grade your paper. If you only describe the process, your answer is safe, sure, but it's incredibly shallow. But on the flip side, if you jump straight into a deep explanation without even naming the core concept first, your answer just sounds totally confused. For example, imagine a classic past paper question about sound storage. A description, the what, might simply say, sound is stored by taking samples of the sound wave. Okay, that might scrape you one single mark. But in explanation, the how and the why might say, sound is stored by an ADC, an analog to digital converter, measuring the amplitude of the sound wave at regular predefined time intervals, which is known as the sample rate. These specific measurements are then converted into binary values so the computer's processor can effectively process and store them. Do you hear the massive difference there? The explanation doesn't just state an isolated fact, it reveals the entire core mechanism.
Your computer science reasoning becomes significantly stronger, and I mean noticeably stronger, once you clearly understand these key theoretical boundaries. Why? Because they often control the entire direction of your answer. When you are dealing with image and video files, you must definitively know the difference between memory, like your RAM, which is volatile and holds the image file temporarily while you are actively editing it in Photoshop, and storage, like a solid-state drive, which is non-volatile and holds the file permanently even when the power is completely turned off. If an exam question specifically asks how a massive 4K video file is stored long-term and you start rambling on about random access memory, you've crossed the wrong boundary and instantly lost the mark. Boom, gone. Similarly, you have to understand data versus information. Raw binary data, just a sea of zeros and ones, means absolutely nothing to a human until it is actively processed into information, like a beautifully rendered full-color photograph on your monitor. These contrasts are the theoretical foundations that examiners deliberately use to test if you actually understand the architecture of a computer system or if you're just frantically throwing buzzwords at the paper hoping something sticks. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 3. Where students slip. Let's shift gears, put on our examiner hats for a minute, and run an interactive workshop to identify the most common exam errors so you can build a bulletproof, error-aware mindset.
When a senior examiner sits down at their desk with a massive stack of hundreds of papers, they see the exact same errors repeated endlessly, paper after paper. They see students who definitely know what an MP3 or a JPEG is in real life, but fail completely when asked how the computer actually represents and compresses that data internally. These are the traps, which is exactly why having error-aware study notes is infinitely more useful than having beautifully highlighted notes that just list correct facts. Let's do a quick mental challenge together right now. I call this Find the Flaw. Imagine a student, under pressure, writes this exact paragraph about storing a digital image. To store an image, the computer uses pixels. It saves the pixels on the hard drive. A higher resolution is better. This takes up a lot of memory. I'll give you a second. Where is the flaw? Actually, there are several massive flaws. First up, saying the computer uses pixels is incredibly vague wording, means almost nothing technically. Second, higher resolution is better. Wait, better for what exactly? Is it better for image clarity? Yes, absolutely. But it's significantly worse for storage space and network bandwidth. They stated a generic advantage with absolutely no context or technical reason. Third, they confused very similar terms by stating it takes up a lot of memory when they definitely meant storage space. This paragraph is a classic textbook example of missing the crucial steps in the process of how color depth, resolution, and metadata actually multiply together to create the final file size.
Remember this always. Examiners are strictly testing your fundamental understanding of the core mechanism. So whatever you do, don't let a familiar keyword or a shiny surface feature distract you from answering what's actually being asked. Let's do a quick data scan challenge. If an exam prompt mentions storing a week's worth of continuous 1080p surveillance video on a standard USB flash drive, a stressed student might write an entire beautifully structured paragraph about how USBs are solid state, highly portable, and unfortunately easy to lose or steal. They fixated entirely on the surface feature, the USB drive itself. And in doing so, they completely ignored the deeper process, the absolute necessity that a continuous high-definition video stream must be heavily compressed using lossy compression algorithms to even have a chance of fitting onto that limited capacity drive. Seriously, understanding the deeper mechanisms rather than getting distracted by the surface features is exactly what separates an A-star student from a C student.
Section 4. The disciplined path. We know the traps now. So here's exactly how you need to structure your high-scoring answer to avoid them every single time.
To entirely avoid those frustrating mistakes, you need a highly disciplined, logical sequence to follow every single time you see a question about text, sound, image, or video storage. Following this strict path ensures you don't nervously jump backwards and forwards in your writing. Instead, you produce an incredibly clear, logically flowing answer rather than just vomiting facts in a random order. Let's do a speed writing breakdown of how this builds a perfect response. Step 1. Identify the demand. Is the examiner asking you to calculate a raw file size, or are they asking you to explain the analog to digital conversion process? Let's say the demand is explaining how a bitmap image is stored. Step 2. Classify the concept. Okay, we know we are dealing with bitmaps, grids, pixels, image resolution, and color depth. Step 3. Explain the sequence step by step. This is where clarity of sequence really matters. Watch this. First, the image is divided into a uniform grid of tiny squares called pixels. Second, each individual pixel is assigned one specific, solid color. Third, that specific color is represented by a unique binary value, the length of which is determined by the system's color depth. Fourth, all of these binary values are stored sequentially in a file, alongside essential metadata, like the image dimensions in file format. Step 4. Connect it back. You tie that sequence directly back to the scenario in the prompt. Applying these 4 precise steps is how you produce a flawless peel paragraph, under pressure, every single time.
Take a look at this. This is a golden, unbreakable rule straight from the examiner's desk. If you leave your ideas floating around an abstraction without technical specificity, you will absolutely not get full credit. I cannot emphasize this enough to you. If you write something like, "Compression makes files smaller, so they download a lot faster," that is a completely generic response. A middle schooler could tell you that. Instead, to get the marks, you need to say, "Lossy compression algorithms permanently remove non-essential data from the video file, significantly reducing the overall file size, which thereby allows the video to be streamed over a network with lower bandwidth without experiencing excessive buffering." Do you hear the incredible difference in quality there? That second response uses authentic, verifiable computer science terminology. It actively demonstrates a deep understanding of the how and the why. It boldly shows the examiner that you aren't just guessing, you are applying specific calculated logic.
Context is everything. If a question is set in one of these specific real-world scenarios, your written answer must strictly stay inside the boundaries of that environment. Because real-world transfer is what converts raw memorization into actual usefulness. Let's play this out. Say the exam question is about a fast-paced retail environment wanting to store high-quality promotional videos on their main e-commerce website. If you start talking about how amazing uncompressed raw video format is because it's perfect for Hollywood movie color grading, you score 0, nothing. Why? Because you completely ignored the retail website context. An e-commerce website critically needs fast page loading times and low bandwidth consumption, especially for users browsing on mobile networks. Therefore, your answer must laser focus on the necessity of high compression formats like MP4, explicitly balancing the need for acceptable visual quality against the absolute need for smaller file sizes to ensure the retail customer doesn't get frustrated and leave a slow loading page. Real-world context dictates your entire technical strategy. It perfectly forms the evidence and link stages in our PEAL framework.
Section 5. The final system. Let's move to the ultimate self-check mechanism. Here are 4 powerful questions to completely guarantee your exam readiness before you ever hand your paper in.
I want you to think of this as your permanent internal cheat sheet. Whenever you finish writing a long, extended response question on data representation, I want you to stop writing for just a brief second. Force yourself to run your answer through this mental filter. I promise you, this exact filter will catch those vague descriptions. It will highlight those missing steps in the sequence, and it will flag those generic statements that are actively costing you grades. If you can answer these 4 prompts aloud about a complex topic like video or text storage, you are ready. If not, you need another cycle of reading and recall. Let's test it right now live with sound storage. Question 1. What is it? It's the digital representation of continuous analog sound waves. Question 2. How does it work? Well, an analog to digital converter samples the sound wave's amplitude at regular intervals and translates those exact measurements into binary data. Question 3. Where is it used? It's used heavily in streaming services, voice-over recordings, and all forms of digital communication. Question 4. Why is it better or worse? Well, using a higher sample rate is better for overall audio fidelity and accurately recreating the original analog sound.
But it is demonstrably worse because it requires significantly more storage space on the drive and much higher bandwidth to transmit over a network. If your written exam answer organically hits all 4 of these exact quadrants, you have successfully crafted a comprehensive, examiner-pleasing response that leaves no marks behind.
And that brings us perfectly to the 3-pass revision cycle. This is the ultimate time management matrix to ensure you hit 100% of your mark potential. First, you secure the basic definitions. Second, you rehearse the worked sequential explanations. And third, you practice adapting your core answer to widely different contexts. Pass 1 is all about utter clarity, knowing your pixels from your vector graphics, distinguishing your sample rates from your bit depths. Pass 2 is all about the sequence. Can you mentally trace the path of data from an analog microphone all the way through the processor to a binary file resting on a solid-state drive? Can you explain the exact algorithm of run length encoding for compressing an image? Pass 3 is adaptability. This is where you take that solid technical knowledge and force yourself to apply it to a hospital patient database, a restricted school network, or even an automated robotics system. This layered 3-pass structure is uniquely powerful in computer science because these underlying binary and storage concepts are recycled and reused across literally every single chapter of the Cambridge syllabus. Listen, students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly explainer sessions.
I'll leave you with this final, absolutely crucial question to test yourself with today. When you look at a past paper tomorrow, can you apply what you've learned and actually justify your technical choices in a real-world system, or are you just comfortably repeating memorized definitions? Because knowing the textbook definition of a JPEG or an MP4 simply won't save you when the exam explicitly asks you to design and justify a massive storage solution for a global media company. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here.